And I know that it was a little bit out of the blue, just felt like maybe not what we were used to. Hopefully today's stuff, at least I think based on the other classes, today's stuff should make that feel like it has a little bit more context, okay? So we talked a lot about internal energy and how a change in, first, internal energy is defined as all the kinetic and potential energy that a system has. And that specifically, we're going to be looking at how that energy changes from the beginning of a reaction, the reactants, to the products, okay? So lots of times we draw this as an energy diagram and show, okay, like the products are at a lower potential energy here. So if they're going to a lower potential energy, that must mean that energy is leaving the system somehow. Or we could do the reverse and say, we have reactants and they go up in energy to get to the products. So that must mean energy is coming into the system in order for that to happen. And the way that it does that, energy coming in or going out of the system, is through heat, which is Q, and work, which is W. So today we're going to actually calculate values for heat and work. And then we're going to tell you why they're really hard and why we're not going to do it anymore. And we're going to add in a new quantity called enthalpy. So by the end of class, we're going to introduce the concept of enthalpy, and then we really will spend the rest of the chapter, so like Friday and Monday, calculating enthalpy in a few different ways. Enthalpy is basically just going to be heat, but at very specific conditions. And then we're going to completely drop out talking about work. Not that work isn't important. It's like part of our everyday life. You drive a car, you're utilizing work, okay? But it is not nearly as important for a lot of the chemical reactions that especially a biology student would see, not so much an engineering student, okay? So that's why we're going to focus in on the ones where it's heat differences and also these particular conditions that are more frequently seen. Okay? All right. So we're going to start with heat, and to do that, we need to talk about heat capacity. I can't remember if I brought this up on Monday or not, but temperature and heat, we need to be really clear. Those are not the same thing. Okay? So heat is energy that's transferred from one thing to another. Temperature is the measure of the kinetic energy, so how fast the molecules are moving. But if you give energy to two substances, they're not going to necessarily respond. Their movement isn't necessarily going to respond in the same way. So I guess we could talk about this in terms of an ionic compound and a covalent compound. Usually we think about examples with metals. We're going to get to that in a second. No, let me just draw that because I think that'll be easier to move on to the example. So metals we didn't talk about metallic bonding much, but they are basically just all lined up, kind of like an ionic compound is. The difference is that they don't have positive and negative charges. They have electrons that kind of flow over the whole surface. This is why they're able to conduct electricity well, is because the electrons aren't assigned to a particular atom nearly as they are in a molecule. Okay, we do see some of that in molecules, right? Like oxygen holds onto the electrons more than hydrogen does in water, but in a metal, they're spread all over, however big that chunk of metal is. Okay, it's called the sea of electron model. So there's your metal. It has a very different structure though than water would. So water has these individual units, and next chapter actually we'll talk about how these are held together. So these little dotted lines that I'm drawing, they're interactions between the molecules of water, and they're quite strong interactions in water compared to some other molecular substances. But just by looking at the pictures I've drawn, let's say this is aluminum, okay, a metal. they're very different structures, and the way that they're going to absorb energy is related to the differences in their structure. So when I give energy to a piece of metal, how it changes temperature is going to be a lot more dramatic than if I give that same chunk of energy to water. So see the size of the arrow that I've drawn? Let's say that that is a certain amount of heat energy being given to those. You will only see a teeny tiny little increase in the temperature of water. Let me draw that in a different color. So you might see the temperature of water go up a half a degree or 1 degree or something. The metal, though, with that same amount of energy added in, might go up 5 degrees. So this is why it's important for you to realize that that heat going in is different than what we see as the temperature that results because of that addition of heat. And the term we use and the number we assign to every different chemical or every different substance is called the heat capacity. And that basically just means how does it respond when it gets energy given to it? How does its temperature respond to energy being added in? So if we look at aluminum and water, so here's aluminum and here's water. You can see the values are actually quite a bit different, right? 0.9 for aluminum and 4 for water. Now, the technical definition of heat capacity is written right here, this bullet point. You can read it to yourself, but I'm going to go back to the example we just had and show you what this is telling us. It's related to, these numbers are related to changing the temperature by 1 degree. Okay, so we're going to use the same example above, but instead of adding the same amount of heat, we're going to say we want the temperature to rise the same amount. So let's pretend we've got, starting with 1 gram of aluminum and 1 gram of water, because they have to be the same amount of the substance. And let's say that we just want to raise the temperature from, say, 23 degrees to 24 degrees. Okay, that's our goal. So start at 23 and end at 24. So same amount of each substance, same change in temperature. The number on that table will tell you how much energy do you have to add in to get this change to occur. So for aluminum, it says that we only have to add in 0.9 joules of energy. But for water, we have to add in 4.184 joules. So more than 4 times as much energy is necessary to get them to go up the same amount in temperature. So both ways are correct. Thinking about if you add the same amount of energy, one's going to have a bigger temperature increase than the other. Or if you have the same amount and you want the same temperature increase, one's just going to take more energy. It's just this is how it's written in the table. Okay, so the number it tells you is how much energy is going to be required to get it to go up 1 degree. And you can extrapolate that, right? If you have 10 grams of the substance, you can figure that out instead of just 1 gram. Or if you want it to go up 20 degrees, you can figure that out. So there's an equation. You guys have probably used it in that lab that I referenced that you did in Chem 1. And we'll do that in a minute. Okay? So there's a lot of real life examples where you see this. So I get so confused about what did I mention in another class versus what did I mention in here. But if you put a pot of water on the stove and you turn on the burner, that's you're adding heat, you're adding energy into that system. You leave it there for like a minute and come back, the pot is going to be really hot. Like it very well might be well over 150, 200 degrees just after like a minute. Okay? The water is still going to be cold. Yes, some of that is because of direct contact, but more than that, it's about the fact that the metal has a low heat capacity. So even just a small amount of energy sitting there for a while is going to increase its temperature really, really rapidly. The water is going to have energy pumped into it, just to get it to rise, up to its boiling point. So that's like a common one. The other one that you'll see application-wise a lot of times is like if you look at ocean temperatures versus air temperatures. So air has a really low heat capacity. It doesn't take a whole lot of energy to increase the temperature of air, but water, like we saw, is really high. So if you feel the temperature of the ocean, like let's say it's 70 degrees outside, the air temperature in the spring, the water in the ocean is going to be really cold still. And then in the fall, you get 70 degrees and the water is really warm. In fact, even like 50 degrees air temperature, there can be really warm water in the ocean in the winter. Even at 80 degrees in the spring, the ocean water can be really cold. That doesn't really make sense, right? It's because the water takes a lot of energy. It takes like all spring and summer long to get that energy into the water because its heat capacity is so high. And then it also takes a long time for it to cool down. So it'll stay warm for a lot longer than the air will because it holds on to that energy really well. Okay? All right, so let's do a calculation with it. This is that equation. I think you guys have seen this before. So Q equals MC delta T. Don't worry about that S subscript. You'll never see that anyway. And this is the mass of the substance because the amount of it matters. The specific heat, so this is for a particular chemical or compound for a particular substance. It's different. We have some of them on the chart. It might be given to you in a problem. And then the change in temperature. So how much is the temperature changing by? So keep in mind, this is a change. And we said change is always going to be final minus initial. So in this case, temperature final minus temperature initial. So go ahead and take a minute or two and solve this problem here for a sample of iron. Calculate the heat for this process that they're describing using that equation. Aren't equations nice? We didn't use equations at all in Chem 1, really. The sig figs on this one are dumb. I'm not even going to include it because it's technically would only be 2. Okay, so biggest mistake people make is they invert the temperatures, right? You're so used to being like, oh, it's got to be the big one minus the small one, right? No, we have to keep it final minus initial if you want the sign to be correct. So when this says negative 3,954.5, does it mean a negative energy? Like, what does that even mean? No, it means the energy is released. That's what the negative is telling you. So when you look at that, you think that amount of energy is released or given off. That should make sense because the sample is cooling down. If anything's cooling down, that means it's giving off the heat that it has, right? So it's important as you're going through these to like calculate the correct sign. And the way you do that is by the change is always final minus initial. And conceptually, you should make sure that you have the right sign, okay? You should look at it and say, well, is it going from a high potential to a low potential if you're talking about a chemical reaction? And in fact, if you're doing this for a chemical reaction and you get a negative sign, that's telling you it's going down in potential energy. That's really useful conceptual information. Okay. All right, we good with this so far? Okay, let's do a more complicated one. So we're not going to do this part at the bottom right now. I'm going to give you a problem you can do later on with that if you want. We are going to look at this. I should have made this picture bigger, but this situation here, we're going to take a chunk of hot metal. We don't know what the metal is, and but we know its mass and its temperature, 44.7 grams, 76.2. So it was a hot piece of metal when we started. You stick it in water, a certain amount of water, 32.8 grams, and you know the temperature, and then you let them equilibrate. This is true of any two substances you put in contact. You leave them long enough and their temperatures are going to be the same. If you stick an ice cube and warm water and put them together, the ice cube is going to warm up and the warm water is going to cool down, right? Until they're the same temperature. That's what equilibrating is. So this one comes to 29.2 degrees at the end. And it wants to know the amount of heat that was transferred. Now, this is probably just like the absolute value. The sign here is not really relevant. It's like, if this is, my 10 joules of heat, I give it away. So technically my Q would be negative 10. The surroundings would be positive 10. But the amount that was transferred is just 10, right? So they just want to know the number. They want to know how much heat is transferred. So initially, you should be like, there's a lot going on here, right? Also, how can we do this if we don't even know what the metal is? This is trying to introduce you to the idea that if you don't know something about the system, because we're not going to be able to measure temperature directly of a chemical reaction, so we can't know everything perfectly about a system, we can infer it from the surroundings. So think of the metal here as the system and the water as the surroundings. What do we know about the surroundings? We know its mass. We know its initial and final temperature. And we know how it responds to removal or gaining of heat. We know its heat capacity. So we can actually determine the Q of the water here. And we know that if one thing gives away heat and one thing takes it, that amount has to be the same. The sign will be different because one is releasing it and one's absorbing it, but the amount is going to be the same. So we can simply rely on the fact that it says here, the Q of the metal is equal to the Q of the water, just a different sign, right? So we're going to go ahead and just calculate the Q of the water to determine that amount of heat. So go ahead and do that, and then I'll tell you another problem that, I don't know, we might have time for. We'll see. But go ahead and figure out the amount of heat that's moved from the metal to the water by just looking specifically at the water itself. So be careful when you're doing this that you're using the mass of the water, that you're using the specific heat of the water and the change in temperature of the water. If you need to remind yourself by putting subscripts there, do so. So as you're finishing up, check your work, check your answer. Now, if you were given something in kilograms, obviously you need to change it into grams. The units are always given by the constant. So like this is joules per gram degree Celsius. That's how you know it needs to be in grams. That's how you know that the temperature needs to be in Celsius. Now, technically, in this instance, since it's a difference, you could get away with leaving it in Kelvin, but maybe don't do that just because you don't want to confuse yourself later. Sometimes you'll see specific heat capacities given in moles. This is usually like for gases this will happen. So it might say joules per mole degree Celsius. So you need to transfer that into moles or convert the grams into moles if that's what you're given. Okay. So 810 joules is being handed off from the metal to the water. That's why the metal's temperature decreases, the water's temperature increases. So we're not going to do the calculation, but I want you guys to just think through how you would do this, and then I'll kind of leave it, for the sake of time, I'll just leave it for you guys to do on your own if you want. Think about how could you figure out what metal this is, because it says it's an unknown metal. So what your initial thought should be is, well, what do we not know about the metal that could help us identify it? That specific heat capacity is a key indicator of it's unique to substances. Now, there is some overlap. I didn't realize this until I looked back in my other class. Lead and gold apparently have the same specific heat. So if it was one of those, then it would be, you wouldn't know exactly. But if you were to take this relationship, you know that water, the Q of the water was 810. So the Q of the metal is just negative 810, right? That's what this relationship means. So the same value, just different signs. So you actually know the heat now of the metal. You know its mass, you know its change in temperature, so you could go and figure out the heat capacity. And if we're lucky, it'll be on the table and you could identify the metal. okay? So key takeaway here is this relation, not only the calculation, but this relationship between two substances, a system and surroundings. They're going to have the same amount of energy. It's just the sign is going to be different. One's absorbing, one's releasing. Okay, now we're going to move on to work and do a couple calculations with that. So did we look at this picture last time? Yeah? Okay. Useful. Thank you. So we talked about the fact that work is related to gases, and they have to be in a closed system so that they can either expand or contract. So it's a little creepy, but picture yourself inside of a container and you push out on the sides of the walls. Okay, so it's closed, but you're able to push on the walls. So if you're the one pushing on the walls, that takes your energy, right? You're having to push the walls away. That is the force that's being applied. So you're the one doing the work, which means that your sign of work or energy would be negative. Energy is going out of you. It goes into the surroundings. So that's why the expansion of a gas is the gas doing work. It is pushing out on the sides of the container. So just a reminder there, we did talk about this one before, but I know there's a lot of new information. So work being negative is it's done by the gas because it's pushing against something else. It's losing its energy because it's using it to push against something else. If the surroundings pushes in on it, so some other force pushes those sides of the container in, that's when work would be positive. There's actually energy going into the system in that instance. Okay, so like I said, this is a closed system. That means that the pressure is not constant. That's going to become important when we talk about enthalpy. Because a constant pressure is one in which gases can equilibrate with each other. And so there's not a buildup of pressure in a particular place. So this is definitely not that. It's calculated also by a pretty straightforward equation. Work is equal to negative P delta V. Okay, so whatever pressure is being applied or is being caused by the gas times the change in volume. So how big or small does that volume get? And then the negative sign is what's going to make it the correct either work being released or done. The only thing about this is the units are weird. So we're going to do pressure in atmospheres and volume in liters. And the unit you get is liter atmospheres or atmosphere liters, whichever way you think of it, which is actually an energy unit, which is very weird. Someone asked in my other class, they're like, how is that an energy unit? That's not kilowatt hours or calories or something. So if you remember, work is force, something pushing, times a distance, how much it's being pushed by. So in physics, you might do this Newton meters, right? Newtons is the force, meters is the distance. In this case, the force is the pressure, right? It's pushing. And the distance is three-dimensional because it's pushing in all directions. And so that's why it's change in volume. So you can actually tie it back pretty easily to a very physicsy way of looking at energy. But the problem is we're usually using this in terms of heat as well, which is in joules. So you're going to have to convert that most of the time because you can't add things together if they're not the same units. So this conversion factor is on the exam equation sheet. Basically, when you use this equation, if it wants it in joules, you're going to then have to convert it or multiply by 101.3. Okay, so let's do an application of this one. And just make sure you answer it in joules. Okay, let's go ahead and take a couple minutes for that. Same thing with the change, final minus initial. You want to always make sure you're doing that. Every time you see that triangle, delta, final minus initial, final minus initial. Okay, so you should get negative 150. So negative means that the energy is leaving the system. Let's double check and make sure conceptually that makes sense. The cylinder, blah, 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 expands from a volume of 1 to 2.5. So it is pushing out, okay? So that makes sense. Work is being used by the system or given off by the system to the surroundings. So it should be negative. Okay. Last one kind of related to this. I'm not going to give you a whole lot of direction on this. This is kind of bringing together a bunch of the concepts. Just go ahead and calculate the delta E for this situation. There's your first little reminder if you're lost. But don't forget to pay attention to the sign. Okay, so a system loses that much heat. So it's leaving the system. So that should be negative 487. So this is like turning words, interpreting a situation into values. So negative 487 for the heat. And the work, at first it says, blah, 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 does 125 joules. No, the surroundings is the thing doing the work. It's doing the work on the system. So that means the energy is going into the system. So that's going to be positive. Okay, so there's heat energy leaving the system, but work energy coming in at the same time. Okay, so you should have an overall change in energy of 362 joules leaving the system. So you'll have examples in the homework where it's like it'll make you calculate the heat and the work and then calculate the change in energy. So like a 3-step process there. And like I said, I would just refer back to Monday's notes to kind of put this all into context so that the concept stuff that we talked about on Monday now makes a little bit more sense now that you've applied it to real situations. Okay? So in the last few minutes, we're going to end with talking about, like I said, this special form of heat that we're going to use for the rest of the chapter. So I want to recap the idea of state functions because this is really kind of important part of this, why we use enthalpy. So remember we talked about state functions at the end of class on Monday. Maybe you were starting to get tired, so we'll review it a little bit. But state, that term, means that it only relies on the initial states and the final state. So if I have reactants and products for internal energy, which is a state function, and for this quantity we're going to talk about now, enthalpy, also a state function, we only care about what is it initially and what is it finally, okay? We don't care about how it got there because there are intermediates in a chemical reaction. There are different ways that we can chemically get from reactants to products. We sometimes represent this like by saying, okay, maybe this is one direction. It makes something up here that's higher in potential energy, and then it goes lower, and then it finally goes to the product, okay? Or maybe it's like it goes really low in energy and then back up. So for energy and for enthalpy, it's irrelevant which direction it took, which path it took. It only matters where it started and where it finished. Heat and work, though, are not state functions. They would change. The amount of heat transferred would change if it was the green path or the purple path. Okay? So it is very complicated and very circumstantial, like depends on the individual circumstances when you're looking at heat and work. So although they are important in certain situations, they're beyond the scope of this class because it would get really complicated really quickly. The other thing is this idea, this term enthalpy, because it's a state function, it makes it a lot easier, and it's widely applicable to a lot of common chemical reactions, okay? So key point is that enthalpy is a state function, so we can do a lot of simplifying of calculations, and that's, like I said, that's what we'll do for the next couple classes is calculate enthalpy. But what is it really? That's the other thing we need to know. It is heat. It's just heat at a very specific circumstance. It's heat at constant pressure. So if you remember, I said we were talking about work, and I said it's in a closed system and the pressure can build up. A constant pressure is one that's like open to the atmosphere where pressures can be exchanged, gases can be exchanged, and that changes how the heat behaves. When we have it at constant pressure, we then see that it is path independent, okay? It doesn't matter the path it takes. So we give it a special name. We call it enthalpy. It's with an H is the abbreviation or the symbol. And it corresponds directly to the potential energy difference between the reactants and products. So conceptually, that is a really important component too. So if a reaction says, oh, I have an enthalpy change of negative, 2,000 joules, that tells you that the reactants are at a higher potential energy than the products, by 2,000 joules. It tells you something about, how those reactants and products are staggered. Okay? Kind of related to that, and we did this earlier a little bit, but this idea of a difference in potential energy becomes really important too when we start to predict what types of chemical reactions will occur. So this first example, and I think you guys have heard this term, but exothermic. Did I already talk about this at the beginning of class? Geesh, it is like all gets so muddled over the 3 classes. So exo, think exit, thermic, heat. So heat is exiting the system. This is just like we saw before. We're just very specifically applying it to enthalpy now. But if you've got the reactants at a higher potential energy and they go to a lower potential energy, that difference in energy, specifically heat energy right now, that is equivalent to the enthalpy. So whether that's 10 joules or 1,000 joules, the difference between those two. And because the heat would have to be given off for that change to occur, then the enthalpy value is going to be negative. Opposite would be true. If you're going up in potential energy, that difference would then be positive by however much that energy difference is. And we call that endothermic. So heat would have to be coming into the system. And the exothermic one, the one where energy is released, that is the most favorable condition. That is where we see chemical reactions most likely occurring. Why? Because you've heard me for like a semester and a half now say things tend to lower potential energy, right? In fact, you should be asking yourself, why in the world would the one on the right ever happen? Why would anything ever go up in potential energy? Well, there's more to the story. There's another component to why chemical reactions happen. It's called entropy, enthalpy and entropy. So it's another part of the story that we're not going to talk about. But just know that this is the more favorable type of chemical reaction where energy is released because it's going down in potential energy. Okay? So we'll spend 2 more classes calculating actual enthalpy values. All right, I will see you, today's Wednesday, I'll see you on Friday.